So, you have seen in the last lecture how we can create lattice registry across the interface, and that is how we can create coherency along the interface. But you know, it is may not be always possible to maintain this lattice registry. So that is mainly because the plane spacing along the interface may be varying too much, and this will lead to large difference in the atomic spacing, and this can lead to a situation where it is no longer possible to maintain the coherency. So, that is what I have written here. Strain is basically taken from the book directly. Strain associated with the coherent interface will increase the interfacial energy of system, but sufficiently large misfit means sufficiently large variation of the interplanar spacing, it becomes energetically more favorable. It becomes energetically more favorable to replace this coherent interface with semi-coherent, in which lattice deregistry is periodically taken by the dislocations. Okay. Basically, what does it mean to say is that suppose if we keep on increase these difference of the lattice planes, I mean to say the distance of the lattice planes here and there in alpha and beta, if we keep on increase that, after a certain time it will be possible to maintain the interface coherency, but bonds will get distorted too much. So, you cannot actually accommodate so much of the strain in the distortion of the bonds. It is not possible. If the bonds are getting distorted too much across the interface, it is better for the system to actually create dislocations along the interface, a few dislocations, so that this distortion can be accommodated. Other places a complete lattice registry can be maintained. Okay. So that the distortion which is happening across the plane from left side to right side for all the atomic planes are now reduced only to the dislocation cores. That is the major difference which can happen. So, matching in the interface is almost perfect. You see here it is perfect here, perfect there, many places except dislocation cores where structure is distorted. So, instead of making all the planes across the interface distorted, we are making only few places distorted. That is energetically more favorable. So, let us first describe, because we need to go into different formalisms, what do you mean by misfit? Misfit is obviously coming from the difference of the interplanar spacing. So, as you see, delta is always defined as a symbol for the misfit. It is defined as a d beta minus d alpha by d alpha. Okay. So, d beta is the higher value, the atomic spacing is higher for d beta and alpha. It can be other way also, negative and positive, both misfits are possible. So, d alpha is a interplanar spacing of matching plane in the alpha phase, and d beta is the same thing corresponding to that. So, then we can define delta as the misfit, and this is always terms as a percentage. That is why you write 100. Okay, that is what is the way it is defined. Now, how does it affect the boundary energy? Okay. In one dimension, lattice misfit is completely accommodated without any long range strain field by set of dislocations, and the dislocation obviously has to be accommodated. This basically looks like a low angle gain boundary. There are a lot of dislocations, and the spacing between dislocation is defined by d beta by delta, okay, where delta is the misfit. So, as the d beta increases, that means distance between the difference between the two alpha and beta planes spacings increases, this d will become smaller. In other words, in unit length there are 1 by d alpha and 1 by d beta arrays of alpha beta respectively dislocations. So, there are 1 by d alpha minus 1 by d beta vacant arrays of beta in the unit cell, which is equal to the number of misfit dislocations in the unit cell. Well, what does it say? See, d is nothing but what? If you put down d, what does it become? You can clearly see d is 1 by alpha minus 1 by d beta. Basically, d is like this, 1 by alpha d alpha minus 1 by d beta. Okay. Now, if I do the mathematics properly, I do get d beta by delta. So, when delta is small, that is misfit is very small, then d alpha equal to d beta. So, therefore, then is d beta become Bazar vector. Okay. So, that is why when the misfit is very small, it is you need only 1 or 2 dislocations to along the boundaries to create such a kind of interfaces, and then energy of the boundary is slightly higher than the coherent boundaries, but not much. Okay. That is what happened in many of the superalloys, where this misfit is so small that either one or few dislocations enough to create this such a kind of boundaries, and these actually are very stable boundaries. Well, I am talking about only one dimension, right, only along one directions, but crystals are not, they are actually 3 dimensionals. So, let us talk about only 2D, what happens. In a practice, actually misfit usually exists in 2 dimensions or in 3 dimensions, okay, in some cases, but for the sake of understanding, let us assume misfit is only existing along 2 dimension, and along 1 dimension z axis, let us suppose there is no misfit, it is perfect match, it is a coherency. So, the coherency strain field can be completely relieved if we have, then to have to relieve that we need 2 sets of dislocations, one set of dislocation along the x axis, other set of dislocation along the y axis, that is what is shown here. Okay, and you see there is this is along x, this is along y. Okay, that is what is shown, sorry, this is along x and this is along y, that is shown delta 1 and delta 2, because both the directions there will be lattice planes may not be perfectly matching, there will be misfits, and therefore, based on the misfits we need 2 sets of dislocations. The moment the dislocation spacing is more than beta, b is basically Bazar vector of the dislocation by delta, the coherency strain will have been only partially relieved by the misfit dislocations, and there will be residual strains. Residual strains mainly because of the distorted bonds, okay, because it is more than b Bazar vector by delta if this dislocation spacing, still some bonds, it has already been shown here, I can go back here. This, because although these dislocations are created to relieve the strain, but still there are few bonds like this one along the core of the dislocation, or this one, they are having distortion. Although dislocations are existing only in 2 places, but the bonds are still, some bonds are still distorted. This can only happen when the spacing between these dislocations is basically more than Bazar vector b by delta. So, therefore, interfacial energy of a semi-coherent interface will have 2 parts, right. One part is chemical contribution, that we have seen for the coherent interface, that is the difference of the atoms in the across the plane. On the beta side you have one kind of atom, white atoms, on the alpha side you have a black atom. So, that leads to chemical part. Second part is known as structural part, what is given as gamma st, which is the extra energy due to structural distortion caused by the misfit dislocations. So, chemical semi-coherent interface will have chemical part and the structural part. Now, chemical part is obviously because of the change of the bonds type, okay. AB bond has been is the main bonds across the interface, but the structural type, structural part, which is this gamma st, for small value of delta, that misfit, the structural contribution interface energy approximately proportional to the number of dislocations or density of dislocations. Okay. Obviously, more number of dislocation, more is the dislocation course, and more is the energy of the structural part. Okay. So, that is basically understandable. Therefore, I have written here gamma st, the structural part is proportional to 1 by d. 1 by d is the distance between the two dislocations, or is basically proportional to delta, because 1 by d is proportional to delta, because d is proportional to 1 by delta, d is equal to b by delta. So, therefore, d is proportional to delta. So, therefore, more is the distortion, more is the structural part. That is understandable clearly, because the delta is the misfit. So, more is the difference between the interplanar spacing of alpha and beta, more is number of dislocations are required. Okay. But you can also have semi-coherent interface along the 3 x, y, z, then you need another set of dislocations along z axis also. So, the more number of dislocations along the 3 axes, more is the energy of the system. That is the structural part of the interfacial energy will increase as you have such a kind of situations. But in metallurgical systems, normally coherency is perfectly mentioned along one of the axes, either x, y, z, and other two axes can be semi-coherent or it can be completely incoherent. Okay. So, therefore, I can actually do a little bit of maths. This is basically coming from literature or whatever, understanding of the measurement of energies or calculations. Gamma actually, when the misfit state increases, gamma increases rapidly. As you see here, that is because you are creating dislocation in one side, other thing you are making this some of the planes, atomic plane bonds distorted. But it has been seen that when the delta has a critical value, which is known as, which is about 0.25, when this reaches, then the misfit energy becomes constant, it does not increase further. Well, the misfit dislocation, as the misfit dislocation decreases, associated strain field, okay, that is mainly because again coming from the lower gain boundary discussion, as you create more number of misfit dislocations or decrease the misfit dislocation distances, after some increase of number of dislocations, their strain field will start overlap, and the moment the strain field start overlap, what will happen? Negative and positive strain field may cancel each other, and these can lead to leveling of the misfit strain energies. So, that is why you see the misfit strain is about 25%, 0.25, sorry 2.5%, not 25, 2.5% of misfit strain is what is to which normally the interface misfit strain energy increases, after which it becomes constant. Energy of a semi-coherent interface is normally 200 to 500 millijoule per meter square. Now, let us discuss about the third case, which is known as incoherent interface. Okay, we have seen coherent, we have seen semi-coherent. What is incoherent interface? When the interface plane has a very different atomic configuration in the two adjacent places, completely different atomic configuration existing between the adjacent planes, and there is no possibility of good matching. It is impossible to do that, and such a kind of pattern of atom can either be very different in both the phases, or it is possible that interatomic distances may differ more than 25%. Once is shown such a kind of thing, you see here the atomic arrangements or atomic configuration in both the phases alpha and beta, this is beta and this is alpha, is such that there is no way we can match the atomic planes. Okay. There is a little match here, but slowly the matching has gone completely out of the way. So, therefore, almost most of the atoms across the interface are not satisfied by the other side of the crystal, other side of the phase. Okay. So, alpha atoms, that is black atoms, are not at all forming any bonds across the interface. So, that is why these interfaces are actually called incoherent interface, because there is no lattice registry at all we can think about it. Please try to understand there is very little has been research on such a kind of interfaces. We know that such a kind of interface do exist, but little atomic structure of these things are not known yet, and they will have very high energy, about 500 to 1000 millijoule per meter square, which is important thing is that is insensitive to the orientation. It does not matter what is the orientation, energy will remain constant, same. We have seen that depending on the orientation of the crystals, of the phases across the boundary in both incoherent and semi-coherent, the energy can vary, but here that is not the case. It is just like a high angle gain boundary. High angle gain boundary also energy of the boundary, it does not matter what is the orientation of the crystals across the boundary. Same thing happens here also. Now, upon giving you some idea, let me talk about a very special cases of semi-coherent interfaces. As you see, to have a semi-coherent interface, you need to have certain kind of a atomic planes across the interface between the two phases must have certain kind of arrangements. But semi-coherent interface can also form between phases when good lattice matching is not initially obvious. That is, these are the systems who exist in metallurgical systems. Let me give an example. Let us talk about in a iron, steel. FCC is a gamma phase, gamma iron, gamma solution of carbon in FCC iron, and BCC is suppose alpha. Okay. So, 111 of FCC is a closest packed plane, but 110 is not a closest packed plane in BCC. But there is a orientation relationship in which has been given by long back by Nishiyama and Wasserman, that says that 110 plane of BCC will be parallel to 111 plane of BFCC. Whenever such a planes will be parallel across the interface, there has to be one direction which will be also parallel, otherwise it is not possible to dictate exact orientation relationship. So, in 11001 directions contained in the 110 BCC structure is also parallel to 1 bar 01 contained in the 111 FCC plane. Or it can be that the first relationship is maintained like in Kurzumov and Sachs relationship, which is KS type, but the planes, the directions contained in both the planes parallel in this case are different. Here actually 1 bar 1 in the BCC is parallel to 0 1 bar 1 plane in FCC. The only difference between these two is rotation. Okay, you try to understand this aspect very clearly. Difference between these two in both the cases actually. Difference between both the cases is basically that the closest packed planes actually varied about to 5.26 degrees Celsius. Let me explain it carefully. If you look at carefully here, this is 111 plane of BCC, okay. This is 110 plane of FCC. The difference between these two orientation is about 5 degrees, okay. That means I can actually superimpose atom in the FCC crystal with the BCC crystal in such a way that the directions will be only varied little bit. That means atoms are there existing across the plane, but directions are about at an angle. If they are falling on each other, then it was a perfect match, but in such a case it is not possible because of the atomic planes and such were oriented. So, only possibility that to create a semi-coherent interface here is to have a little bit of angular distortion between the directions in the FCC and the BCC crystals. So, they are actually not parallel exactly, specifically telling they are parallel in such way, but they are actually in one direction, other direction there are angular relationship. So, because of that you see here that here in some regions the atomic planes are not matched. Here you see they are not matched, okay. But here they are matching. Actually we are looking from the top. If you look from the top across the interface, wherever the black and white atoms are falling on each other, that means they are perfectly registered, perfectly bonding each other perfectly, there is no distortion much. Wherever they are falling apart, that means in this place or in this place they are falling apart, that means they are not matching each other, there is a gap between the two planes. So, even after angularly distorting the directions of the plane by 5 degrees, it is not possible to have a perfect match of the atomic planes across the interface. Some places atomic planes will match, some places they will not match, but still it is better than a complete incoherency. In complete incoherency there will be no match at all, okay, we have seen that. Compared to that, this is much better situation, energy can be still lower, that is why they have said complex semi-coherent interfaces, the special type of. A coherent semi-coherent interface between the two bound phases is impossible for large interfaces parallel to 111 in FCC and 110 FCC. Such interfaces will be obviously incoherent if the distances are very large. Okay. Now, there is another important concepts, let me just another few minutes I will just introduce the concepts, and this is basically coming from book of Reed-Hill, Physical Metallurgy Principle, Robert Reed-Hill. You know, these concepts actually known as coinciding sides boundaries. Long back both Kornberg and Wilson actually showed that the rotations can produce surfaces separating the new crystal from the old that contain a number of positions where atoms in both crystal were coincidence. Okay, let me just go back here. The reason I brought up these concepts in this case, both NW and K's relationship, is basically that even in this atomic distribution or atomic configuration, some places atomic planes are matching, some places they are not matching. So, wherever these atomic planes are matching, that means their atomic bonds are actually coinciding. Wherever they are not, they are falling apart, they are not coinciding each other. That is exactly is the idea of Kornberg and Wilson. They said that rotation can produce surfaces separating the new crystal from the old, or maybe two phases that contain a number of positions where atoms in the both crystals will coincide, but other places they will not coincide, and these positions are known as coincident sites. Okay, the kind of lattice we create is known as coincident site lattice. Net A, I do not know whether you can see here, net A correspond to white atoms and net B correspond to black atoms here. See, net A corresponds to the atomic arrangements on 111 planes of FCC. 111 planes of FCC are actually, you see, they are hexagonally oriented if you carefully look at it. Okay. And net B also corresponding to 111 plane in a secondary recrystallized crystal out of FCC. I do not know that now you have no idea of recrystallization, but let us suppose something has formed from the crystal, first FCC parent crystal. These two nets are rotated relative to each other by 22 degrees across 111 directions. That means, if I have two nets, one net, other net like this, I rotate by 22 degrees one net with respect to the other along one of the axes, and let us suppose the axis is the body is diagonal of the FCC, body diagonal is along 111. So, if I rotate along 111 one of these nets, then I can bring some of these planes, some of the atoms coinciding with the parent crystal. That is what is known as coincident site lattice. So, I can actually rotate in certain angles, those angles will be particular values. You cannot rotate along certain all angles, there will be certain angles in which you can rotate one of the lattice planes with respect to the other lattice plane on a certain axis and bring this kind of coincidence. This is possible actually in many cases, and when I do that, I create special boundaries. There will be cases which I will show in the next class, the boundaries will be perfectly matching, atomic resistivity will be perfect, and obviously because of that energy of this boundaries will be lower. The basic idea is that I can rotate the one plane with respect to other, just like you see in NS and KS type of relationship I discussed in the last slide, where the 5.260 rotations of the 111 the planes along 111 directions can lead to certain kind of match of the lattice planes in certain positions. So, that leads to reduction of the interfacial energy. This is possible to extend, this idea can be possible to extend to further to create different kind of boundaries, and these boundaries are also known as coincident site boundaries or special boundaries. Okay, let me stop here because these concepts are actually very difficult, and in the next class we will talk about how we can create such a kind of boundaries and how can actually we can discuss about the different relationships in the next lecture. In fact, in next two lectures I am going to complete or wind up interfaces and start discussing about real phase transformations afterwards. Okay.